So, polynomial functions. Not that foreign of a topic. We've been dealing with polynomial functions pretty much throughout algebra. Talking about a power function, any function in the form of f of x equals a to the x of n, where a and n are non-zero. If they were zero, then we would have not a polynomial function, and it would be possibly equal to 0 or just 1. And then for a power function, a is the leading coefficient and n is the degree. Now, what does that mean? We've been doing things like this. F of x is equal to x squared. In this, we know that technically there is a 1 there, and the 1 is my leading coefficient. And the degree in this case is going to be 2, because that is the exponent, the value of the exponent. Now, and a power function has a positive integer and is called a monomial. So just understanding what that is, and we're going to do some examples here, but just being able to understand that a polynomial function may be a different degree, and it's going to have characteristics based on its degree, and some of them will replicate, and it's once we start to learn it, see the patterns, and it becomes a lot easier. Now, this is what we were talking about earlier in the term, where we talk about x as x approaches negative infinity as we go this direction. It looks like y is, so understand what this is by in behavior statements. So they said when a monomial function is even, so when my degree is even, right here, x squared, it could be x to the 4th, x to the 6th, and so forth. So when it is even, I'm going to have this general in behavior. As x approaches negative infinity, y is going to approach infinity. As x approaches positive infinity, y is going to approach infinity. So this is in behavior. That's what they're saying, is x approaches negative infinity, f of x approaches infinity. The domain for my positive even integers here is all real numbers, because it goes forever and ever that direction, forever ever in that direction. The range, in this case, the range is going to be all real numbers greater than or equal to 0, because the function does not exist down here. It starts at y equals 0, and then goes to positive infinity. So understanding that. Let's see here. So that's the general even. Now, if for some reason we have, this is, my coefficient is a positive 1/4. If I have a negative, then it flips. So it reverses. We've been doing this kind of transformation and understanding those things. That a, when my a is negative, right, it's going to flip and go downward. So the domain is going to remain the same. The domain is going to remain the same. The range is going to be all values less than or equal to 0, because it starts at 0 and then goes to the negative. And then my in behavior, as x approaches negative infinity, I'm going to negative infinity. As x approaches positive infinity, y is going to negative infinity. So that reverses on my domain and range. For odd functions, so in this case we have x to the 5th, x to the 3rd. That could be actually x to the 1st, y equals x. It could be y equals x to the 7th, and so forth. Any of those odd exponents, we're going to have this general flow, where as x approaches negative infinity, my in behavior, y is going to approach negative infinity. As x approaches positive infinity, going this direction, y is going to approach positive infinity. And if you think about it, the general, this is, if I just sort of took and created this line, this, connected 2 points, that is basically sort of looks like a linear slope is positive. So if that's going to be the general for any of these positive odd degrees, are going to have this same general in behavior. And of course, for these all real numbers for my domain, all real numbers for my range, because it goes on forever, left and right, up and down. So that's why all real numbers for my domain and range. This one again is a positive coefficient, leading coefficient. This one is a negative leading coefficient. So above it looks something like that. When we have a negative coefficient, it flips and goes to, think of it this way, that's a negative slope. Okay, and that reverses my, or changes my in behavior. So as x approaches negative infinity, f of x approaches infinity. As x approaches positive infinity, f of x approaches negative infinity. And nothing changed though. My domain and range is still all real numbers. So looking at that now, I did add a couple over here. Now they've really shown these to us, but just seeing that, let me put these on the graph real quick. Now these are obviously not drawn to scale, they're not exact, but I just wanted to give you the general idea of my in behavior. So as I have x to the first, I have that's the general, in behavior. As I'm going to positive infinity, I'm going to positive infinity. As I'm going to negative infinity, I'm going to negative infinity. And then showing you that when I have a negative a, so this is instead of a positive one, I have a negative one, it flips and I'm going the opposite direction. Here where I have x squared, I go upward, and I have domain is all real numbers, and then my range starts here and goes upward. But here, as I have a negative, it flips and goes the opposite direction. So just seeing that, that's what's happening here. Again, x to the third has this general shape. And then when I have negative x to the third, I have it going to the opposites. Same thing with x to the fourth, where I have x to the fourth would sort of make a W shape. And then I would reverse that when I have negative x to the fourth. So just seeing that and understanding what's going on. And I will tell you that to look at this, I'm trying to show you that technically in factored form, I have 4 roots. This is all of these. I have 3 roots, up to 3 roots in factored form for the cubed. Just like we know for a quadratic, we can have up to 2 roots, showing you the factored form. So just keep that in mind, and trying to tie these understandings together. Now that was a lot of information, but coming here in behavior of the degree of a monomial right here. Leading coefficient is -2, so we know that it has been reversed. The positive cubic looks something like that. So then the negative would again look something like that. So -2 is my leading coefficient, so it was reversed. The degree is 3 because that is the degree of that monomial. And my in behavior, looking at it on the graph, helps me to see that as x approaches positive infinity, y approaches negative infinity. As x approaches negative infinity, y is approaching positive infinity. And then my domain and my range are both all real numbers for my odd degree polynomials. So here, the x to the 6th, that's even. It's a negative coefficient, so the f of x equals -10x. So it's going to look something like this on my graph. Not trying to scale, of course, but knowing what do my evens do as x approaches, I can just do that, say that's my x and my y. As x approaches positive infinity, y is approaching negative infinity. And then as x approaches negative infinity, y is approaching negative infinity. So my range, in this function, actually, the range is going to be y such that y is less than or equal to 0. If you put that in the graph, you're going to see that it only goes to the origin I did this to exaggerate the 6 roots. And then the domain, of course, is going to be all real numbers for all of my even functions. There you go, tying all of those little things together. Graphing a power function using a table. Well, just like anything we've done, let's see here. For water to flow through a garden hose at a certain rate of gallons per minute, it needs to have a specific pressure in pounds per square inch. Through testing and measurement, the company that produces garden hoses determines that the pressure P, given the flow F is defined by P of F equals 3/2 F squared. So the function, the pressure is determined by the 2/3 times the flow rate squared. So that's what we're talking about. Looking at this, I should know that's an even function. So I should know, state the domain and range. If it's an even function, I should know my domain is all real numbers. All real numbers. Now the range is going to depend on where does it start. Did it reach 0 when I plugged in values for my flow? It turns out that I do have a low point here when x is 0, y is 0, and then everything else is going up. So my range is actually going to be for all values of y such that y is greater than or equal to 0. That's my range. And of course, this is simply putting values in for x, getting y out, or putting the flow in, getting the pressure out. So, and then they turned around and graphed it so we could see what was going on. Now here, talking about graphing those. Again, all of those characteristics help us by understanding the end behavior, understanding the leading coefficient, understanding what the even and the odd functions do helps us. But degree and leading coefficients, it says state, well here, standard form, the degree of a polynomial is n, leading coefficient is a to the nth. Continuous function that can be described by a polynomial equation in one variable. So this is not a polynomial equation because there is more than one type of variable. You have x and y. That's why it says it is not a polynomial. And let's see, we'll work with the rest of these and see what's happening. Now that normally we should be written in the order from greatest to least. That's just standard form, and we see it when we have x squared plus x, minus 2. We know that, that we naturally just put it into descending order. But the degree, state the degree and leading coefficient of each polynomial in one variable. Degree of 4, leading coefficient of 2. Degree of 3, leading coefficient of 7. We said this is not a polynomial because it is not one variable. And then here we have the degree of 5. Leading coefficient is 1. Because if there's not a number out there, we know that it should be a 1. And let's see what else. And select the degree and leading coefficient. Are we allowed to have negative exponents? Because that could be rewritten as negative 6x to the negative first. Because it is in the denominator, and it says non-negative. N, which is my degree, is a non-negative integer. So here, this is a positive integer, so that should not be a polynomial. Right here. It is less than 0. So that does not make a polynomial. Otherwise, had that not been there, we would have said that this is my degree of 3 coefficient of 11. That would have been the answer had it not been for this. Okay. Moving on here, evaluating a graph. Well, evaluating a graph, we've been doing that, in algebra, where we would have f of x equals, and I'll just use this one again, 2x minus 2. And then they say, hey, find f of 4. And that just means we take 4 squared minus 4 minus 2, because wherever there is an x, they want us to put in a 4. So we replaced all of our x's with 4s. That is evaluating the graph, or evaluating a polynomial function. So here in this density of the sun in grams per centimeters cubed, expressed as a percent of the distance from the core of the sun to the surface, can be modeled with this monster polynomial. 519 x to the fourth minus 1,630 x to the third plus 1,844 x squared minus 889 x plus 155, where x represents the percent as a decimal. So we know that if we are talking about a percent, we are going to need to convert it to a decimal. And then at the core, x is 0. At the surface, x is 1. So find the core density of the sun at a radius of 60% of the way to the surface. So you got to write it as a decimal, and just understanding when I have 60%, that is 60%, which is equal to 0.6. Okay, you can put it in the calculator, 60 divided by 100, 0.6, but understanding that is 0.6. So they replaced all of my x's as a decimal with 0.6, and then they turned around and evaluated it and came to 0.6224 grams per centimeters cubed. Okay, that's what they did. Sketching that graph, if we look at the table, we can generate this table in a calculator, come up with some points, and then log and graph them. And it's difficult for some students at this point in time to graph, right? They're like, oh, I don't know where this decimal's at. We just got to estimate, okay? We just got to estimate. I know that it's about 82, about 83. Well, if this is 90, then it's somewhere about right there, okay? It's a little bit closer to 80 than it is to 90. You would be wrong. When would you be wrong? You'd be wrong if you said, oh, it's up here, because that would be wrong. That's 90 something. So it is an estimate. Even if you look here at 0.4, when x is 0.4, it looks like they're just at like 0.3 or 3. So yeah, they're about 3, because that would be 10. It's an estimate. So that's what it would look like. Now here in this check, I would encourage you to do this check on your own, but you want to look at that function notation. To help predict heart attacks, doctors can inject a concentration of dye in a vein near the heart to measure the cardiac output of patients. In a normal heart, the change in the concentration of dye can be modeled with this function, where x is the time in seconds. So x is the time in seconds. Find the concentration of dye after 5 seconds. So they want to replace x with 5. Wherever there is an x, you put 5 in. So when you two ways to do this. This is what I would do. In y1, put it into the calculator, and you have negative 0.006 x to the fourth plus 0.140 x to the third minus 0.053 x squared plus 1.79 x. Put that into the graphing calculator. Okay, so the reason I put this into the graphing calculator is just because it allows me to see, I had to go back and fix the function. If I make a typo or if I do something wrong in the calculator, then it's really just sort of shot. And if I forget to put my number in parentheses, if it's a negative, there's a lot of errors that can happen that way. But once I put it into y equals, I can look at the table and see that after 5 years, what is the concentration after 5 years? 5 seconds. It should be 21.375. Okay, so that's 21.375. If I needed to look up multiple seconds, I have it right there in my table. The work's already done for me. So then as I look, and again, if we look in this next step, right here it's saying, hey, select the graph of the concentrate of dye over 10 seconds. So where are we at after 10 seconds? Let's see. What would be logical for me? We want to make sure that when we set, let's see, the time, number of seconds, right? Seconds, the concentration of dye. So it's going to be one of these two. Because this is concentration. The input of concentration is not the output seconds. So that's how we can eliminate these two. So if we turn around and just think, well, when it was 5 seconds, it was approximately 21. Sorry, that's all messed up. When at 5 seconds, it was approximately 21. Over here, 5 seconds is approximately 8 concentration of dye. So this would have to be the right graph that I was looking for. Okay, so just understand sometimes it's a little bit easier to do just by having a good idea. So your input of seconds would be my x value, so that just immediately eliminated those two. Okay, so the zeros of a polynomial function, remember the 3-4 things you had. We have zeros, we have roots, we have x-intercepts, and then we have zeros, roots, x-intercepts, and solutions. Think about it. Okay, all of those are the same thing. So when we talk about roots, we are talking about the x-intercepts. So using this, use the graph to state the number of real zeros of the function. Well, how many times does it cross over the x-axis? 1, 2, 3. Those are my 3 solutions. Those are my 3 x-intercepts. And so we can see that there are 3 real solutions. That's what they're talking about. If I were to look at one that might be a little bit different, imagine if the graph did this. It could be the same general shape, but what if it did this? It is a cubic function, but it only crosses over one time. So we only have one real root. The other roots are complex or imaginary. So just keep that in mind that when you have a cubic root, ideally you have a maximum of 3, but you could have less. So just being able to understand what that root and solutions are. And then here I can see that the graph, the number of zeros of the function, 1, 2, 3, 4 roots. So the function has 4 real solutions, 4 real zeros, which means it could be something like x to the 4th. I know, looking at what we learned a little bit ago, I know that, it's a W shape, which is to the 4th power. I know that it's an even function because both things are going upward. I know then that the coefficient is a positive number because both of my n behaviors are going to the positive. So there's a lot of things that we can glean from this N4, this image. And let's see here, going on, comparing the polynomial functions. So I have 2. Let's see here. Examine f of x, and g of x. So it looks like this is g of x, this is f of x. And if I were to fill in some information real quick, okay, so I filled that in off the graph, substitute the values in, okay, create your table, okay. Analyze the extrema. Well, the extrema, I can see we're going back to mins and max. This is a relative minimum. This is the minimum. This is a relative maximum because this function doesn't have a maximum because we continue going into the positive forever and ever. So that would be my extrema for that g of x. This one has a relative minimum, a relative maximum, but does not have a minimum or maximum because they keep going forever and ever in the positive and negative. So that's some of the extrema information. And then, so the relative maximum is approximately for f of x, the relative maximum is approximately y is 6, and g of x's relative maximum is y is 2.5, or I guess they said 2. It occurs between 2 and 3, right? So about 2.5. So blank has the greater relative maximum, f of x. f of x. So we're just comparing functions by, the information we know. Comparing the zeros, x-intercepts and y-intercepts, the end behaviors. The zeros of f of x, I have -3, I have 0, and 1. Those are my zeros. -3, 0, and 1. For g of x, you have -1, -0.5, 1, and 2. -1, -0.5, 1, and 2. The intercepts, x-intercepts, the x-intercepts are going to be the same. Those were my zeros. And then the end behavior, f of x, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity. Okay, so let's see here. As x approaches negative infinity, y approaches negative infinity. As x approaches infinity, y approaches infinity. For g of x, we're going positive, so we're going to be approaching positive infinity on both cases. So there you go. We need to be able to understand, using those characteristics, those definitions that we've used all along, being able to put information into the calculator, leading coefficient, your degree, all of these things come back into play. Your extrema, that relative min and max, all of these things, we just carry them forward and we just keep applying that information. So we'll get some practice in class and see how it goes.